Okay, so hello everyone. I'm Paulo, Fernando. We work here at Klarna, and we want to talk about a project that we worked on a couple of months ago and what was the process behind it. So the talk sounds a little bit off, like what the hell, it seems to be very hyped. Universe as a function. So a little bit disclaimer, there's going to be some graphs, so be aware. So who here is familiar with No Man's Sky? Oh yeah, so a lot of people. So No Man's Sky, it's the premise of the game is that you have this infinite universe that you could basically explore, and then you will see different planets, and you could do anything. You can name planets, animals, and do everything in this infinite universe. So we got inspired by this idea, and we tried to do our own poor man's sky version of it in JavaScript. So this is what we got. So this is we built in NodeKnockout this year. So you are the last survivors of a dying alien species. Your home planet has died. So you have a number of people in cryo, and you need to find a new planet to set up a home. And while you do that, you can also construct Dyson swarms around stars to collect energy from them to keep your ship operational as you find those planets, which are not easy to find, that are suitable for the type of life of your species. So that's pretty much how far we got in the game. And an interesting thing as well is that it has a time arrow. So the stars, they go from accretion disks, they evolve to their main sequence, and they evolve to red giants or supernovas and black holes. And in the top there, you can see you go from the day one of the universe all the way to the heat death. So this is a project that was done by me, Fernando, and also by two people that's here in the audience. One is Tulio, who's there, and the other is Nicola. So if you have any questions, comments, or whatever, feel free to ping any of us about it. Cool. So an infinite universe, you say. Okay. So what does it mean to be able to build an infinite universe? So when you think about building a game, usually what you end up doing is basically someone would go there and basically place things everywhere. So if you think about a file describing a universe, someone would have basically to go there and write every single star, every single system that exists in the universe. So if you want to build this hugely large and infinite universe, it's impractical to basically write this file by hand. So the idea is pretty simple. So instead of having this gigantic file, you have kind of a function that you would call, and this function will give you the universe. And this function is just a basic set of rules that would operate and then give you the universe. So that's the basic idea. Cool. So trying to think small. So the universe is a pretty big thing. So let's start to thinking about the smallest thing that we have in our universe, which is something like a star system. So star system in our case, because if we reduce a lot the amount of data to describe it, could be just two properties maybe. So we have just the star radius in this case, which is 20 pixels, and two planets in orbit. And this is what we would get with this data, right? So if we go to try to do a procedurally generated star system, what we could do is just wrap a function, and then this function returns pretty much that object. It's a procedure-generated planet. It's a pretty boring one because basically you would get always the same planet all the time, but it is a function that returns a star system. So the universe will have pretty much the same systems everywhere. So then if you ever use the Math.random, you would think, okay, this is pretty simple to fix. Then we just use the random function that is available already in the browser. And then, for example, you could see that star radius there, we're generating a radius between 10 and 20 pixels. So random, from those who don't know, it's a number between 0 and 1, so it's normalized. And we're also generating the number of planets there, which is between 1 and 4. So these are the different planets that we generated by calling these functions 4 times. So a side effect of this way of implementing things is that every time I call this function, it will return me a new system. So it's not repeatable. It's impure. So you can see here, so the problem that this brings is if I visit a part of the solar system, I would see a star there now. If I go away and then when I get back, I'll basically see something different. So this doesn't work. So what we need?
Yeah. Hello. So what we need in a way is to control this randomness. So we need to generate systems from random seeds, from random information, but we need in a way to be able to generate the same thing from this random function. So saying control randomness already sounds like a contradiction. So how can I control something that is more or less by definition unpredictable? The thing is that we have to think what randomness is, and especially what randomness is in the context of a computer. So the thing is, within a computer, there is no real randomness. There is only very hard to predict sequences of numbers. So the thing here is that when we see something like Math.random, there is no actual randomness because the computer cannot generate that. The computer pretty much computes stuff. So what we need is something to generate, something that we cannot predict. And when we talk about predictability, so let's see how a regular function that we use to looks like. What we say that in this function is we can predict easily what's going to be the output of the function. It's not just that we can compute it, but also let's say that I know the value of y for x 100 is going to be 50. Okay, so I know the value of y for x 200 is going to be 100. I can more or less know what the value of y is going to be for x 300, and so on. But if you think about this function instead, it's a little harder to find a pattern. So that's what we mean by unpredictability. For every value of x, if I know the value of x for 100, I have no simple way of knowing what the value of y is going to be without actually computing the function. So that is to say, because this is not actually random, if you look, this is what is called a pseudo-random function. But if you look at plotting this same function twice, if you look, for example, at the corners, at the bottom left corner, you can see that there is a point in 0, 0, and it's there both times, because this is just a pure mathematical function. So that is completely different from Math.random. So you can take a look here, for example, in the upper left corner, that there is a dot in 1 in the right side, but in the left side there is a gap. These are going to plot different things each time because Math.random is not a pure mathematical function. In a way, it's not well behaved. We cannot repeat the sequence that we got out. So what we want to do instead of using Math.random is to get some sort of repeatable random. We call it repeatable random. There are a lot of functions that behave like this. You might, functions that behave like this. Very common ones are SHA-1, SHA-256, and so on. So in this particular one, we're using a seed that is just a number, so it's a different one. But what you get now is that you need to pass a parameter into the generateStarSystem function. It's no longer an impure function that returns something. You need to pass a parameter, and we show it in the graph. For example, the 026 is going to give that system with that radius of the star and those 3 planets. So that's all fun, but here we plot a lot of them. And can you spot a problem with this one? Sorry? OK, so let's take a look, for example, at a big star. So let's say the big star in the second row. It has 4 planets. Now let's take a look at the second star in the second row. It has also 4 planets. It's big and it has 4 planets, and so on. Can you spot a big star with 1 planet? Yeah.
Oh, no, I was thinking just to use the random. You see the all the time.
You mean, let me see something. You mean in here?
Yeah, I mean, usually you see it with 1 random first.
Yes, exactly. I'm using the same seed. That is exactly a problem. I'm going to show that here. Thank you. So the problem that we have is that there is a correlation between the size of the star and the amount of planets. This is a problem that we can have by naively replacing Math.random with a function like this. So what you can see here is that for different values of x, when the amount of planets goes down, the radius of the star goes down. So there is actually a one-to-one correlation. These two functions, these two curves are different in amplitude, but it is exactly the same otherwise. Yeah, and this makes sense, of course, because what you were saying, the seed is the same. We use the same seed for the same function. And since this is a pure function, we could, for example, calculate it once, and it will give us 0.8, for example. And it's 0.8 times 10 plus 10, and the other case is times 3 plus 1. Either way, it's going to be the same value that we multiply, so there is going to be a correlation. But that is not what we want. We want the universe to have big stars with a single planet and so on. So how can we solve this? So we need to decorrelate the values. This is like a little more tricky than what it sounds, because you could think, okay, I just multiply the noise that I get from the random function, this 0 point something a number I multiplied, and I will get something different. But actually, it will still be correlated. So what we do is to add a unique factor to the seed. So this unique factor, since this function is very unpredictable, if we sum 1 to the seed, it will already give us a value that we have no idea what it's going to be. So, but if we add a different value, a very unique, the problem is that if we add a 1, for example, it's very likely that at some point in the program, in other place, we also do plus 1. So these values have to be unique. We factorize the seed by some value. We add something to the seed. It has to be unique, because otherwise we're going to keep using the same seed, so we get the same number in some other place in the application. So we'll still be correlated. Ideally, these numbers should be extracted as constants, and so we make sure that they are unique. So after we do that, this is the same function plotted using the unique, like salt, if you can't. And what you get here is that there is no visible correlation between the two. So of course, they could have some correlation. This is like a predictable function, so of course, it will have like a, if you look close enough at some point, but it's good enough for our game. And when we run it again, we can see that there are small planets with a lot of, small stars with a lot of planets, and bigger stars with only one planet, and all the variations.
But I was promised the universe, right? Like, that's the topic of the talk. So far we're talking only about solar systems. So how do we get from all these star systems and get to the universe scale? So here's a universe for you. So that's the universe. So following the same concept where we have a function to generate the star system, which is just a parameter, which is the seed, we can put this one level up, and now we have a function that takes one parameter as well, and then it generates systems for us based on this parameter. So, but when we think about like how do we go and like distribute all the stars throughout the entire like universe, so it's easier to think about splitting up the entire universe into smaller quadrants. So a quadrant here is just a slice of the universe defined by some coordinates, which in this case is 0, 0 there at the top, and some size, which is 800 by 400. In our universe, each pixel is actually 1 unit of dimension, so it's a good correlation. But still, like if you were to try to calculate the stars for this particular quadrant, we could just ask for each individual pixel if there's a possibility for being a star in there. But that's just too many pixels to ask for a star. So for example, for this small quadrant, there would be 480,000 possible stars that could appear in this particular quadrant. So we want to reduce this to a much more reasonable number. So what we do is pretty simple. We just break it down into smaller pieces. So in this case, we just break this quadrant into like smaller sectors, and each sector can have only one star. So there you go. So we have our stars in each one of these quadrants. That's all good and great. So what do I do now is that for each one of these dots, I use again the random function to generate another noise for each one of these. So then, now we have like each one of these dots, they're actually define a star system. So we have a star system 0, 92, 95, 81, 32, and so on and so on. And then we grab this noise, use the function that we already described how we can create, and then we get into the star systems for a universe. So each one of those numbers are translated directly into each one of those star systems. But still, this is pretty boring, right? Like the universe is not exactly a table. So we want things to not be so like fitting into this grid. So it's also, again, very simple to circumvent this issue by just like snapping them from the grid. So again, we use over and over the random functions and composing them over and over, with just getting more noises out of noise to get here and get another noise so that we move X and Y slightly inside this grid. And once we do that for each one of these systems, then we get them slightly snapped which one of these sectors. And now we have a universe that is at least not as uniform. So without this set, now what we can do is we can pretty much use this universe function that I can pass some coordinates, I can pass the size of the quadrant that I'm seeing, and I can basically, if I start moving and I start calling these functions over and over again, I would be basically getting new systems as I'm moving, and the other systems that I'm not seeing, they basically don't exist. So it's quantum mechanics. If I'm not observing, it doesn't exist. So only what you're seeing is what exists. And if I rerun this function again, we will see the same thing again. So if we go to this coordinate, like tomorrow in another computer, we'll be seeing exactly the same thing. Cool. So that was fast. So wrapping up, if anyone is curious, like this was built around this stack. So we're using React for the rendering. The entire app is basically SVG everywhere. It's just SVG. We turn into SVG freaks to make this work, understanding projections and all that crazy stuff. The state management is actually Redux, which we tried to push how we could make like a game with Redux. We use Ramda, of course. Alea is the random implementation that we use. It's an NPM package. And Sagui is a project to manage the build process of the app, so we don't have to deal with Babel, Webpack, and all that stuff. Cool. So if you're interested in this project, I did a lot of hackathons in the past, and I've tried to basically put together all the smaller projects that I've did. So with other people. So there's this website, Macaco Maluco, which means crazy monkey in Portuguese. So if you're interested, like all the projects are open source, they're all running, all Docker containers, all good. So feel free to play around. And before we go, like I like to make an homage to this. He's a best friend of mine, like from childhood, that passed away last week. Yeah, he was very important to me, and he teach me to programming also. So yeah, so he passed away last week. So I don't know if this means something, but yeah, thanks, man. Cool. So yeah, we'd like to thank Nicola, of course, for putting this together, and Jonathan and Klarna for hosting and employing us. Yeah, and questions.
Is this on? Yeah, it is. Okay. You catch? How did you avoid like overlapping the stars after they were moved, so they don't like intersect, or did you avoid that?
Yeah. So in the actual game, the grid size is a little bigger, and we do have a cut factor, so not every grid space has a star. But for the demonstration, it looked too empty, so we snap it smaller.
Hey.
I think it will be nice to show the demo of the game actually that is online. So one fun thing is that it's not just the procedurally generated universe, but also like the life cycle of the stars systems, which is also implemented. Like they start with accretion disks, they end up into stars, they blow away, they end up into.
It will probably blow the presentation to discuss time exactly, but it's also procedurally generated the time. So that time function was also part of the definition of the star system.
If we rerun this again, it will be exactly the same thing. So the stars are in exactly the same place. They pop up at the exact same time. Yeah, you can see like it's exactly the same thing. So it's although it's procedural, it is defined. So it's not predictable. It is, yeah, you know what I mean.
I think like the chaining of the noise functions was one of the most significant learnings of this, because what made possible to have these systems that look very different even if they use a single seed. Well,
what took the longest, the SVG graphics or the randomness?
The randomness.
yeah. Randomness, I think, yeah.
Yeah, we pretty much mobbed the whole thing. So it was basically 4 of us sitting in a couch. Yeah.
Okay, I'll use this one. If there's no more questions, we'll go for let's say 10-minute break and meet here again 5 past. Let's meet here again 10 past for Johnny. Okay, thank you very much, guys.